So today we're doing the HSTAT Review for Chapter 3. So start with, a lot of nice facts about correlation. Read those. Definitely want to know those. Correlation questions are pretty common. It's one of the main concepts of the chapter. First one, correlation between the heights of fathers and heights of their fully grown sons is R equals 0.52, so moderate. It would be the strength there, and it's positive. The value is based on both variables measured in inches. If the father's heights were measured in feet, so we do some conversion there, and the son's heights were measured in furlongs, each furlong equals 7,920 inches. The correlation between the heights of the fathers and the sons would be, and the answer there would be unchanged. So converting doesn't change the R value. Even if you have X and Y here and you switch X and Y, like you put the X there and Y there, that doesn't change the R value. So neither one of those things changes R, which is kind of interesting. The following scatter plot presents data on wine consumption in liters per person per year and death rates from heart attacks. So just looking at the scatter plot there, it looks like there's a negative correlation. In other words, the more wine you drink, to an extent probably, the less your death rate is from heart attacks. Okay, well that's interesting. These data provide strong evidence that drinking wine actually causes, that's a key word there, has a moderately strong correlation, right? I mean, you've got kind of moderately strong there, but is it going to cause? Does correlation prove causation? And the answer certainly would be one of those. It's going to be no. Oh, sorry, I didn't see that's a no. Countries that drink lots of wines may differ in other ways from countries that drink a little wine. We can't be sure the wine accounts for the difference in heart disease. And that's actually the key of it. I think that's actually the answer there. R does not equal -1. That's true, but it's moderately strong, so that's not the reason. Causation that's not the reason. You need experiment, a treatment there. You can't just have correlation to prove causation. The plot shows that the difference among the countries are not large enough to be important. I don't know about that. The plot shows that the deaths go up more for alcohol from wine. Deaths go up as more alcohol from wine is consumed. No, that's clearly wrong, right? That's just not even accurate to what's there. Consider the following scatter plot. A lot of scatter plots here. The amount of carbon monoxide and nitrogen oxide in grams per mile driven in the exhaust of cars. The least squares regression line has been drawn in the plot. Again, negative correlation, moderately strong maybe. In the scatter plot, the point indicated by the open circles, you're talking about that point right there, in case you don't see it, has a negative residual. So we know when it's below, it does have a negative residual. So I think that's the answer. Has a positive residual, like one of these guys, this would have a positive residual there. Has a 0 value for the residual. This would be a 0 value for the residual. It's on the line. Has a 0 value for the correlation. Correlation, that would be like if just completely scattered, like there's no pattern, then 0 would be the slope of the line. It would be 0 for a correlation, no correlation. It's a high leverage point. So a high leverage point is a point that's way off to the right or left, like the X value is way different, and it would have a major impact on the slope of the line. That's not the case here. There doesn't seem to be. There might be an outlier, like this might be an outlier, or this might be an outlier. Or at least they're close to being outliers, but there's no high leverage points there. Agricultural economist says that the correlation between corn prices and soybean prices is R equals 0.7. So positive and moderately strong. So, as one is increasing, the other one is increasing, or vice versa. When corn prices are above average, soybean prices also tend to be above average. That seems to be true. There's almost no relation. Now that would be an R value of 0. When corn prices are above average prices, no, that's a negative correlation. When corn prices go up by $1, corn prices go up by 70 cents. We don't even know the units of these, so definitely don't know that. Economists are confused because correlation makes no sense in this situation. No, I mean, it makes sense to do a scatter plot. I don't think that's true. Just trying to show you maybe why some of those are wrong. The study is conducted to determine if one can predict that the yield of a crop based on the amount of fertilizer applied to the soil. The response variable, so we're going to predict the yield of crop. So remember we call that, so yield of crop is the measured, we're predicting the y value. Remember we have that equation y hat equals a plus bx, right? We predict the y value, so yield of crop is being predicted, and the response variable is called the y variable, so it's got to be yield of crop. If you want to know what goes down here, that would be amount of fertilizer applied to the soil is what it says there, based on the amount of fertilizer applied to the soil. The table and scatter plot below shows the relationship between the student enrollment in thousands and the total number of campus property crimes, burglary and theft, in 1 year for 8 colleges and universities in certain U.S. states. The equation is that. Okay, so we have that. Looks like a strong positive correlation here between the amount of enrollment and the number of property crimes. That makes sense. You would have more crime, but there's more people. With the slope line change at the point 26,601 was removed. So if we took this point away, it's not part of the data. To me, the line would probably be, I don't know, something like that. So the slope would change quite a bit here. So would the slope be less? So we would lessen the slope. You want to say this in a sentence in context, but that's the idea of it. The value of r squared is 0.801. Interpret this value. So you would say start with something like 80.1% of the variation in y, a number of property crimes, can be explained or accounted for by the regression line. I'm not going to write the rest, but I said it. That guy selects a random sample of 100 students in grades 10 through 12, asks them their year in school and whether they are involved in in sports of any kind, or in intramural sports or no sports. Results are summarized in the segment bar graph below. Okay, so we have the seniors, different things. Right away, you can see that it seems to make a difference whether you're a senior or junior or senior or sophomore as to what kinds of sports you play or if you play sports at all. So it does make a difference. So more seniors are involved in interscholastic. So that's this. No, that's definitely not true. There's no association. So no association would be if all the charts, if you had each bar graph kind of had this look to it and they were all kind of the same. Does that make sense? So if that's the case, there would be no association. These are all different. So there is an association there. That's important for you to know. So there actually is an association. That's why that's wrong. There were more seniors in the sample than juniors. We have no idea how many seniors or juniors were in there. It doesn't tell us the number, it just tells us kind of percentages there. Juniors have the highest percentage of participation in intramurals. So intramurals is the X one. Juniors, yeah, that's longer than this, longer than this. That seems to be true. Less than half of seniors are involved in any kind of sport. No, more than half. I mean, these are all the sport folks, and there's only a few that are not no sports. So those are the no sports up there. So that's not true. The least squared regression line for predicting weights of basketball players based upon their heights was computed, and further analysis yielded a residual plot shown. So in other words, we don't see the actual, like the height here and the predicting weights. We don't know what this actual scatter plot looks like. This is not the scatter plot. I need you to understand that. This is the residual plot. Remember when the line's straight across, you're thinking, oh, this is a residual plot. We don't know what this actual data looks like. Although, by looking at the residual plot, we can tell something. Do you see that curved pattern there? So there does seem to be a curved pattern. The residual plot confirms no. So we want to see scatter. If we want to say that a linear model is appropriate, we want to see a scattered residual plot. We don't see that. The curve pattern in the residual plot suggests that there is no association between the weight. That doesn't actually say no association. So just a linear model is not appropriate. That is true. So when you see a curved model in the residual, I don't know what this actual data looks like, but it's probably curved in some way. I guess it would be more dots here, but there's some kind of curve to it, and then you're trying to fit a line to that, and it'll have that kind of a look to it. There are not enough data points. I don't know. I mean, there's plenty. The linear model is appropriate because there are approximately the same number of points above and below. That's always true with the residual plot. Well, not always true. I should say the positive residuals add up to be the negative residuals. Usually they're similar, but sometimes you have some residuals that are really longer than others, and so you don't need as many to make those add up to 0. Okay, so SAT practice, to get some extra practice, I love that. Students in an SAT prep class took 2 versions of the SAT math section on the same day. The scatter plot shows the relationship between the scores on the first practice test and on the second practice test. On y equals x is that red line there. It's included along with the vertical line separating. So these are kind of the bad or poor students who didn't do as well on the test. So these are the weak students, their scores anyway. And these were the strong students on the scores on the SAT. So of the 4 students who scored less than 500 on the first exam, so what percentage scored higher in the second? So that's interesting. So because the second is the y-axis here, these 3 students scored better. So 3/4 or 75% of the students who scored weak on the first test scored stronger on the second exam. Of the 7 students who were strong, so it looks like 1, 2, 3, 4, 5. 5 out of 7 scored worse on the second exam. When they scored pretty well in the first, they still didn't do bad on the second, but compared to the score in the first, they're below the y equals x line, so they're 5 out of 7 did that. This is a good example of regression to the mean because 75% of the students in the weak category did better on the second test, and about 71%, 5 out of 7, of the students in the strong class did worse on the second test. Actually, one was about the same, so it's even worse than that. That's a great example of regression to the mean. If you do really well on the first test, you might not do as well on the second. You might regress towards the mean. If you do really bad on the first test, you might improve. That's just, but in the middle, you see how there's about equal a number on each side of the y equals x line. So that's more what you might expect, about the same number of folks on each side, but not on the ends. It's regression to the mean. Okay, this is a really good question to get you ready for stuff here. So go to your calculator, go ahead and type in the data here. So for your x, at the top, you're going to type in height and type in all those data values. And I'm just going to shoot and type in all those data values. I already typed them in a minute ago. Okay, describe the relationship between height and their shooting percentage. By the way, we probably need to choose an x and y. I think we're going to try to predict their shooting percentage. So this is like our x and this is like our y. So our explanatory variable is height, and our measured response variable would be a shooting percentage. In other words, maybe if you're taller, you shoot better or worse than people who are shorter. I don't know what's going to happen here. Although I will say this, typically, not always in the new NBA, but typically in the NBA, the bigger guys shoot closer to the basket. So they might play on the inside, whereas the smaller guys might shoot from the outside. So the big guys might have better shooting percentage. I'm not sure. Let's just go ahead and graph this on our calculator. So if you choose, I guess we said that the height was the x value, and the shooting percentage is over here. And it does seem to have a positive correlation. Describe the relationship. So let's describe that those 4 things. So it does look linear to me. It looks linear. We might be able to do a residual plot. If you want to do the residual plot, well, first let's do the regression line. So I like the a plus bx one. So it even says the r squared value there. That's very nice if you have your settings set to that. If you want to look at the residual plot for fun, residuals, residual plot. The residual plot looks pretty scattered, right? So I'm pretty happy with that. I'm going to Control Z to undo that. But so I think it's definitely linear. The residual plot is scattered, so it's definitely linear. It looks, moderate or moderately strong. I think either one of those would be acceptable. The R value is 0.7, so that's right in that kind of moderately strong type area. Let's see, there doesn't seem to be any outliers. It's definitely a positive association, strength, form, and so forth. Okay, so what is the equation of the least squares regression line? So we have it there. I'm going to write it the way I want you to write it, which is, so I would say the predicted shooting percentage equals negative 38.4149 plus 1.1013 times x, which is the height. So it's much easier. Otherwise, you have to define your x and define your y values. So just write it like that would be a good way to do it. Interpret the slope. So the slope is this guy, and think of it as a fraction, right? So the x value is the height, which is measured in inches. So this is in inches. And this one is a percentage, right? That y value, that 1.103 is a percentage. That's the shooting percentage. So you would say something in words. I'm just going to say it to you. Every time an NBA player is an inch taller, their shooting percentage goes up by 1.1013%. So that's nice, right? The taller you are, the better your shooting percentage. Does the value of the y-intercept have meaning in this context? So you can't see it really in our graph because we don't see the y-intercept right there. I guess if I grab this, I might be able to change it so we could see it. Look at that. Okay, I see it now. Do you see it? It crosses right there at negative 38. Wow, this is a really bad view of the other part of the graph, but I can at least see the y-intercept. So that means when the height is 0, their shooting percentage is negative 38%. That doesn't make sense, right? You can't have a negative shooting percentage. It's not possible here. Hopefully I did the answer right. Hopefully I didn't talk about height there, but it's definitely, that's the shooting percentage. I'll have to check my answers there. Interpret the slope. So the slope we just did. Does the value of the y-intercept have meaning? No, it does not. It's not possible. Calculate the correlation. Interpret this value. So the r squared value is 0.697. So if I go to like a calculator page, not a scratch pad, but calculator page, you can, in fact, if you want to find that variable, you can actually find r or r squared. I'm just going to show you. R squared is that number. You can also find r right there if you hit variable key. It's that. But if you want to find it yourself, you would go square root, like from the r squared that's on your screen. Might just be easiest to do that. Take square root. Now, it'll always give you a positive number when you square root the r squared value. So you have to be careful. The slope is positive here. That's a positive number. Therefore, the r value is positive. If the slope is negative, the r value would be negative. So be careful about that. If you grab the r from the variable key, you'll actually get it right every time if you have the data. So interpret this value, the correlation. So correlation is 0.835. So I would say two things. It tells you strength and direction. So the correlation is positive. There's a positive relationship between, let me go back to, there's a positive correlation between height and shooting percentage for NBA players. As one increases, the other one increases, and it's moderately strong relationship. So would be the strength. Calculate and interpret the value for the residual for the player who is 77 inches tall. So I'm going to try to go back to this. I'm just going to do a new one. I think it's easier just to click on this one. So I think height was the X. Oops. And shooting. Okay, so I want to do the regression line, a plus bx. Okay, so we've got that equation. So we're going to take that equation and we're going to plug in a value here, right? So you can do this a couple different ways. So if you go to a calculator page, you can actually access the equation. It's called the reg equation, the regression equation, and then put in the number there. It's almost like f of x, and you're going to plug in that value of 77, and it'll give you that value. Or you could do this by hand. You could type in negative 38.4149, if I can type right, plus 1.1013 times 77. We should get a similar number there. I rounded mine off a little bit there, probably, but when you use the one from the calculator, it actually gives you the exact right answer. Still rounded off, but to 4 decimal places. But either answer is acceptable as stats. We're not too picky about that. And so let's interpret that individual that thing. So let's see. The actual was 77. No, it was 43%. And the residual is, or the predicted is 46. And so we have to get the residual. So it's actual minus predicted. So this would be 43 minus the predicted, actual minus predicted wrap. So we have a negative 3.3852. These are percentages. So this person shot 3.3852% below what was predicted by the least squares regression line. Standard deviation of the residuals for the model is 2.12. Interpret this value. So to interpret the standard deviation of the residual, this is the typical deviation or difference from the regression line for all the residuals. That's basically it. Okay, and then table and scatter plot below describe the relationship between latitude and average July temperature in 12 cities. Shown below, does the residual plot support the use of a linear line? It is scattered, so yes. Because the residual plot, that's a residual plot, that's not the actual, that's the residual plot. Because it shows scatter, it is a good linear fit for this one. I wonder if I did put, there was that one question on 10. Can't have a negative shooting percentage. This should say shooting percentage. Sorry, messed that up. And I didn't say what the y-intercept was. Maybe that's why I didn't think about it correctly. But shooting percentage can't be negative, so I had a little mistake there. Trying to fix that. Thank you. That's the end of the